Hi, and welcome to Lecture 5, which has to do with the theory of limits. So this will be a bit more challenging for most of you, I think. We're going to start, though, with something that's not quite so bad. It's actually a little leftover from the last lecture, which I decided I was not going to include this part on the theory of limits at all, and so I was not going to talk even about that one last theorem, which is called the squeeze theorem. The squeeze theorem is interesting because it's one that is not only of interest to people who are theoretically minded, but it's also of interest to very practical people, because the squeeze theorem tells you how to find a limit for a function that's where you can't really tell what it is, and sometimes you can't tell, even with very sophisticated software like Maple or other programs. But you end up saying, okay, this function that I'm dealing with, this f, may be very complicated and I don't really know much about it, but at least I might be able to say it's no worse than, let's say, some function like h. So f you could think of as being dominated by h, but we would say it's less than or equal to h, at least on some interval. So you think of an interval near a, and as long as you're on this interval, the function f might be running around like this, and then the function h is going to be bigger. So let's see if I can get this to work. We might have some red here, and this will be my h function. So you might think that h is like there. All right? But actually, the picture, the situation, as you'll see in a second, is more than that. We want this function f to not only be less than this h, but we want it to be itself, in turn, bigger than some g. So in other words, there's some smaller guy that's down here. So g is here, and f is between g and h. Now that's not so hard. What's a little bit more challenging, though, is that in order to make this squeeze theorem work, not only do you have to trap f between two other functions, but you also have to have the limits of both the outer and the lower and the upper functions. So that means the limit as x approaches a of g of x, and the limit as x approaches a of h of x. These two guys have to have the same limit as x gets close to a. So the picture is not right. This function g has to come in here like this, and the function h, which is on top, has to come into the same limit and still stay bigger than f. So the function h is up here on top, and it's bigger than f. The function g is down here, and it's smaller than f. F is trapped between them, but the outer two functions have the same limit as x gets close to a. So what's the punchline? I bet that you can guess what the punchline is. That if these two functions have the same limit, and they bound the function f, then guess what? The limit as x approaches a of f of x will be equal to the same thing that those two limits are. So whatever number this happens to be, f will have a limit, and its limit will be the same as those guys. Okay, so let me give you an example, just one. There are tons of examples, but this one happens to be one of my favorite functions. Take f of x to be one. Actually, it's one that you've seen before, but I'll make it a little bit easier for this problem. Well, easier to work with. It's the function x times the sine of 1 over x. Now you've played with the sine of 1 over x in the lab, and I had you play with x or x squared times the sine of 1 over x, and I know I talked to a lot of you about this function. What I'm going to do is I'm going to make it even easier to work with, because what I want to do is take the absolute value of this guy. All right? So here's what I'm talking about. This function has a graph which you might remember it's going to oscillate infinitely many times as it comes in here towards the origin from both sides. But as it gets in closer and closer, it oscillates more and more times. Okay, and what you have here in this case is these two kind of invisible diagonal lines that bound the whole curve. Now, all I'm saying is that the curve that I've drawn is in between those two diagonals, and that happens because you're multiplying x times the sine of something. The sine of something spends its entire life between -1 and +1. So if you multiply that something that's never bigger than 1 by x, it's going to be bounded by these two lines, y equals x and y equals -x. So this graph is in here. Now compare this graph with the one that you actually had to play with yourselves, and that is this guy, the sine of 1 over x all by itself. Sine 1 over x just comes in and it goes up and down and up and down, and it goes all the way between plus and -1, and it doesn't scrunch down like this one does. It keeps going back and forth between plus and -1. So in this particular case, the punchline is that the limit as x approaches 0 of the sine of 1 over x does not exist. I'll abbreviate DNE, which many of you use. DNE is does not exist. So the limit of sine of 1 over x as x approaches 0 does not exist. There is no one number that this function gets close to. What about this guy? Well, this function oscillates, but the oscillations are getting damped down. They are becoming less and less and less. And so as x gets close to 0, the y values are also scrunching down to 0. So in fact, the limit as x goes to 0 of x sine 1 over x is 0. Now, I haven't proved this, and plus I'm not really talking about this. I'm going to be talking about the absolute value of it. So if I took the absolute value of this, you just have to erase all this stuff down here, which is negative, make it bounce, it would end up looking like this. Right? So there's nothing down below the x-axis, and then all the graph is up above. So there's nothing down here. So for this function, it's still going to be, but it'll be easier to invoke this theorem. Okay, here's the deal. For this function, if I want to talk about x times the sine of 1 over x, there is this squeeze theorem, which says, can I take x sine 1 over x as a function and say that it is definitely less than something else? And yes, I can, because this function is obviously less than this one. Why? Because the sine spends its entire life between plus and -1. So the absolute value of sine of anything, I don't care that it's 1 over x, anything, is always less than or equal to 1. So if I replace sine of 1 over x by 1, I'm making the thing bigger. So this is a trick that we do a lot in science. This is not just math. This is any kind of science or engineering. We replace something that's complicated, sine 1 over x, by something really, really simple, 1. So if I do that, if I replace sine of 1 over x by 1, what am I doing to the original problem? Well, I'm making it bigger. So x times sine of 1 over x compared to x times 1, if you want to think of it that way, multiply x times 1, then this has to be bigger than x times the sine of 1 over x. I don't care that this 1 over x is going crazy. 1 over x is getting bigger and bigger and bigger. The sine of it is still running around between plus and -1, just oscillating a lot. Okay, but the thing is, if I multiply it by x, the result is going to be less than or equal to the absolute value of x. Now, the absolute value of x looks like this function. It's a v, right? So this function is less than or equal to, x, this is getting too ugly. Absolute x sine 1 over x is definitely less than or equal to absolute x. All right? And it's also obviously bigger than or equal to 0. So all of these oscillations are trapped in here, because obviously the absolute value of anything is bigger than or equal to 0. But look, as x gets close to 0, this is the 0 function. It doesn't do anything. So the limit of 0, of course, is 0. It's a constant. And the limit of the absolute value of x as x gets close to 0, well, that's pretty obvious. So we've got this relationship between this lower function and this upper function, and this nasty thing is trapped between these two, and both of these outside functions have the same limit as x gets close to 0. Therefore, by the squeeze theorem, this function has to have the same limit too. So the limit as x approaches 0 of absolute x sine 1 over x is 0. And then there's a nice little result that says if the absolute value of something goes to 0, well, what about the something without the absolute value? Well, it has to go to 0 in the limit as well. So it's a nice slick argument that shows that this function, x sine 1 over x, has a limit of 0. And this would be very difficult to argue, and even sometimes graphing it is kind of a pain. If you looked at what Maple did, Maple has trouble graphing things when the oscillations are that nasty, and it loses precision. Sometimes it's very difficult to figure out what's going on. But analyzing it is not that bad. You can go back and look at this yourself later on and try to figure out what's going on. All right, so the squeeze theorem, sometimes called the pinching theorem, because you pinch the function f between two things that get closer and closer, and they have the same limit, and therefore f is going to have the same limit. This nasty thing is trapped between two simple things. So this is an example to keep in mind, and it comes up quite a few times. We will see another application of this before too long. All right, time for the main event. So you may want to take a deep breath. This is the difficult part. So what I want to do now is to say exactly what we mean by a limit. What does this mean when I say the limit as x approaches a of f of x equals L? What does that mean? Now, I'm spending time talking about this because, well, first of all, math people have to know it, and people who are not math people also have to know about this. It turns out that if you're not a theoretical person, you care about practical things. And practical things involve nasty stuff like error. And to really understand error, this language is very handy. Now, you may not be talking about limits exactly when you talk about error, but you'll be talking about error in the same way that we talk about limits. So you'll see what I mean in just a second, because we're going to not only talk about the definition, but also look at an example. And there are the exercises that you'll be working in class also focus on this idea. We'll also be playing with this in the next lab a little bit. Okay, so I have to tell you about that definition of limit because it's of interest both to theoretical people and to practical people. And the fact of the matter is that unless I go through this, I don't have a way of answering another question that some of you may have had and didn't want to ask for fear of sounding silly. But hasn't it bothered you that I use language like x gets close to a, f of x gets closer and closer, the y values get closer and closer to L? Doesn't that bother you? Doesn't it bother you in the sense that, well, how close? How close is x supposed to get to a? How close is f of x supposed to get to L? It sounds like we're waving our hands here in trying to talk about these ideas. And math and science are supposed to be quantitative. We're supposed to be able to say exactly what we're talking about here. So in order to put that question to rest, I need to define what is meant by this limit. Before I do this, I have one more thing that I have to do. So I'm going to cover this up and use this page again, except I just want to use the bottom part because I want to introduce you to a couple of letters from the Greek alphabet. Turns out we use these letters and they have a special meaning. We borrow from the Greek alphabet. We borrow from lots of things. But here's the first one. This letter, it's the lowercase letter epsilon from the Greek alphabet. So it looks kind of like an E, maybe a script E. You'll see it written different ways. Some people write it this way. I will write it that way, a little bit more curved. But it's the Greek letter epsilon. And when you see this Greek letter epsilon, I want you to think of the word tolerance or error. One of those two. Keep that idea in your mind. Okay? Then there's another Greek letter that we will use, and I don't draw it quite so well, but it looks kind of like that. This is the Greek letter delta, lowercase delta. You're already familiar with capital delta, which looks like a triangle. But lowercase delta is what we will be using in this definition of limit. And delta also refers to a distance, but it's a distance in a different direction, a different dimension, you might say. But this is the distance associated with the x value. Epsilon turns out to be a distance or an error or a tolerance that you need, and it's associated with the y direction. All right? So when you see these letters, epsilon and delta, then try not to freak out. They are letters. We do use them, and everyone uses these letters. This is very, very traditional. In fact, when you talk about something being within epsilon, that's a very common expression in math and science, and it means that it's going to be pretty close. How close? Well, somebody has to tell you what epsilon is. That's coming up, so you'll see what I mean. Okay, so here goes. What does it mean to say that the limit as x approaches a of f of x is equal to L? It means, and this is a long expression, and all the words are important here, for every epsilon bigger than 0. And when I write this, every time I write this, you should add mentally, no matter how small. Okay? For every epsilon bigger than 0. Don't drop these words. They're important. They're there. So if you just write epsilon greater than 0, it's wrong, because it doesn't say what we are saying here. We are saying for every possible epsilon that's bigger than 0, no matter how small it might be. I want you to think of epsilon as error. How much error are we going to allow? How much tolerance are we going to have? So an example to keep in mind is pretend that you're engineering a machine part, like a bolt, and it's got threads on it. You know, it's a piece of metal that looks like this, and it's solid, and it has threads that spiral around like this so that it can be screwed into something. How well do those threads have to be made? Well, they could be made to within, a billionth of an inch, but that's way too good, and it's not necessary. There could be more error than that, but they have to be made well enough, or else they won't mesh with the nut that you have to screw it into. So the epsilon is the tolerance that we are going to allow when we are manufacturing things. All right, that's just an example, but think of epsilon as error. Okay, so for every possible epsilon, no matter how small, there is or there exists a positive number delta. So for every possible epsilon, there is a delta such that, so that. And here's the punchline. I like to write the punchline first. You can write this in a slightly different way, but I like to look at it this way first. I'm going to write something. I'll say it first in letters, and then I'm going to say it in English. And I'm always going to say this in English, and I want you to also. In letters, this says, obviously, the absolute value of f of x minus L is less than epsilon. I don't ever want to hear you say that. I'm not going to say that again. The fact of the matter is that the absolute value of something minus something is also understood to be the distance between these two things. So let's go back to some scratch paper here. If I just do the absolute value of a minus b, all right, the absolute value of a minus b, what is that? Well, it's either a minus b or b minus a, but whatever it is, it turns out is the distance from a to b. I mean, if a is less than b, like it is on this picture, then a minus b will be a negative, but when you take the absolute value of it, that flips it to positive. So it represents b minus a. If a and b are arranged this way, with b here and a here, then it's the same thing. You're going to get a minus b, so you're going to get a positive answer. Absolute value leaves it alone. So this is the distance between a and b. This is distance. Whenever you have a subtraction of two numbers and the absolute value, you got to read this as the distance between a and b. It's the distance between a and b. And if you don't think this way, if you don't train yourself to think this way, you will never understand what I'm talking about. So work on it. Whenever you see the absolute value of two things subtracted, say to yourself, the distance between this and that. So this says the distance between f of x and L is less than epsilon. Okay, so let's start it again. This statement of limit means that for every epsilon bigger than 0, no matter how small, there is a delta bigger than 0, such that the distance from f of x to L is smaller than epsilon if, provided that, the distance between x and a is less than delta, and the distance, well, x and a are not the same number. Now, there's a lot of ways to say this, and most books, our book does it this way. I will go ahead and do it this way. Bigger than 0. This is strictly bigger than 0. You could also write not equal to 0. Or you could add another phrase that says, and x is not equal to a. Right? Remember, I've said a million times already that the limit does not care what happens when x equals a. That's not the issue. The issue is when x is close to a. How close? Well, this tells us the distance from x to a has to be this close, less than delta, and bigger than 0, not 0. So x and a cannot be equal. So x is within delta of a, but not equal to a. That's what this is saying. All right? One more time. X is within a distance of delta away from a, but x is not equal to a. So that's what we're saying here. So once again, let's read it from the beginning. For every epsilon bigger than 0, no matter how small, we can find a delta bigger than 0 so that the distance from f of x to L is smaller than that epsilon, provided that x is within delta of a and not equal to a. That is the definition of limit. And that is a mouthful. That says a lot. Now I'll try to make this understandable to you. We're going to look at this and tear it apart and put it back together again a billion ways. But let's try to make it make sense to you in a lot of ways. One way I like to use a lot is imagine that there is a boss who gets to set how well your parts are manufactured. What tolerance, okay? So the boss is the one who gets to set epsilon. So the boss, you can think of him as the evil pointed-haired boss, gets to decide that the tolerance is, for example, 0.001, 1/1000th. Okay? So the limit statement would mean that in particular, if the boss chooses this tolerance, we have to be able to come up with a corresponding delta that would work in the sense that if x is within that delta of the a that we're talking about, then the distance from the function to the limit would be within 0.001. Now, how do we come up with this delta? That is somewhat difficult, and that depends on the problem. But sometimes, as you'll see, it's not difficult to do. I think right now we need a picture. So let's let's look at this situation like this. Here's our number a. And we've got our function that's proceeding merrily along like this. This is f. And at this point a, we really don't care what's happening to f. It may or may not be defined. That's irrelevant. But this number right here, just judging from the graph, it looks like that's what the function is getting close to. So this is the alleged limit L. All right? So what has the boss done? The boss picks epsilon. The boss picks a tolerance. So you could think of an example, 0.001. But really the limit says for every possible tolerance. So for 0.001 or for whatever tolerance. So that means that the function is going to have to get close to L. How close? Within epsilon. Within this tolerance. Whatever he picked, I've got to get it in there. Now to show this, I'm going to draw a little strip that's around L. We call it the epsilon strip or the epsilon neighborhood. And all I'm going to do is add and subtract epsilon to L. So I'm going to go to L plus epsilon and sort of draw a dotted line like this horizontally all the way across, and L minus epsilon and draw that down here this way. So here is what I call the epsilon-delta game. The boss has picked an epsilon, like 0.001. You look at your alleged limit and go plus and minus epsilon from there in the y, along the y direction. Remember, epsilon is associated with y values. So your tolerance is this way, vertically, from L plus epsilon down to L minus epsilon. The game is to get this function f within that epsilon strip that goes all the way across, and it's at height L plus epsilon to L minus epsilon. How close do I have to get to A to get all the function values to be within this strip? I'll say that again. How close do I have to get to A to get all the function values within that strip? Well, it's not too hard to answer that question here. If I am this close on the left and this close on the right, as long as my x's are within here, then the y values obviously are within the epsilon strip from L minus epsilon to L plus epsilon. So this is where my x's have to be in order to get within the tolerance. If I want a symmetric interval around A, then I have to pick from here to here. So my delta comes in right now. So from here, this number is going to be A plus delta, and this number is going to be A minus delta. So as long as I pick x's in here, I'm great, because all the y values will be from here to there, and they will be within the epsilon strip. This is the epsilon-delta game. Somebody picks an epsilon, you have to come up with the delta that works. But this has to work for every possible epsilon. But careful, here's how the game is played. Somebody first picks epsilon, then you get to decide what delta is. So if the boss changes his mind and he says, oh, wait a minute, that was pretty stupid. I really meant 0.00001. Okay, so now just imagine pinching those upper and lower bounds so that now they're going even closer, very, very close. So you draw your strip like this. It's horizontal around L. So it's L plus epsilon down to L minus epsilon. All right, and he says, now, you got to do this tolerance. This is my epsilon. He can do that. He can decide to change his mind. But when he does that, you get to change delta. You can say, oh, well, okay, fine. Now my delta has to scrunch way down to here. So my delta has to be this big instead of this big. And we can do it again. If he changes his mind again and cuts down on the epsilon, we've got to be able to show that you can cut down on the delta and still get this to work. There's a picture similar to this in the book. I recommend that you look at this. And several of the exercises have you playing with pictures just like this, where the question says, find the delta that works just looking at the picture. So, on the picture, you look at your epsilon neighborhood around L. That's going from L plus epsilon all the way down to L minus epsilon. Look all across and see how close do I need to get to the A so that all the y values are within the epsilon neighborhood, in the epsilon strip. Okay? So that's the epsilon-delta game for a particular epsilon. Of course, we need to prove this for all epsilons, and this is where the math people have to pay more attention. What happens, for instance, if you wanted to say for this particular function, for f of x equals, let's say, 3x minus 1, and we'll pick a particular a. Suppose that a is equal to, let's say 2. Then how close do we have to get? Well, first, what are we saying? If we take the limit as x approaches a, in this case we're talking about the limit as x approaches 2, and our function is 3x minus 1. What kind of a function is 3x minus 1? That's not hard. 3x minus 1 is a line of slope 3, y-intercept negative 1. So it goes through here, and it's pretty steep, and it goes like that. What happens to this function as x gets close to 2? Well, there aren't any holes in this line. The y values are obviously going to be getting closer and closer to the y value of the point when x equals 2. And when x equals 2, you could plug in 2 into this and get 2 times 3 minus 1, or 5. So, of course, the limit of 3x minus 1 is going to be 5 as x approaches 2. I'm not saying it isn't, but how would we prove that with this epsilon-delta stuff? That's not something that we all are going to rush out and do, but it's something that I think that will help us understand the epsilon-delta game, and it will help the math people especially with understanding how proofs have to go. So just bear with me and follow along. First, we'll do an example, just so that it's easy to understand and with numbers, and then we'll do it again with just letters. Okay? So the example is what happens if the boss picked a nice, simple epsilon. What if the boss picked an epsilon of 1/2? So what does that mean? It means the limit here is L, and we have to get within 1/2 of the L, which is 5. So that means that you have to go from L plus 1/2, so 5.5 up here, to 5 minus 1/2, which would be 4.5 down here. So how close do I have to get to 2? How close do I have to get in here so that my y values are that close? And in this case, it's not too hard to actually calculate. You can see that this function is going up. So my function is 3x minus 1. And where am I when I'm here at 4.5? Where am I when 3x minus 1 is at 4.5? Well, I can solve that for x. Add 1 to both sides. 3x equals 5.5. X equals 5.5 divided by 3. That's what? 1.8 something. Okay, that's good enough. 1.8 something. So when I'm at 1.8, that's on the left. Do it again on the right. 5.5. Where do I have to be to get to 5.5? 3x minus 1 equals 5.5. Solve that for x. So you add 1. This is 6.6 equals 3x. X equals, divided by 2, you get 2.2. 2.2 exactly on this side. So 2.2 on this side, 1.8 something on that side. So this will be the number that I'm going to end up using as my delta. That's how close I have to get to 2 within, well, what is it? The distance from 2 to 1.8. It's a little less than 0.02. So to be safe, I would probably use 0.015. If I'm within 0.015 of 2, my y values will be within a half of L. All right? Let's do it again. This time, we're going to do it in general. So, here goes. The boss has picked his epsilon. Remember, our problem is f of x equals 3x minus 1, and our number a is equal to 2. And the boss has picked his epsilon, but this time he's not telling us exactly what it is. Now that sounds unfair, but I'm going to play his game and beat him at it because I will compute my delta based on what his epsilon is. So, how close do I have to get? Well, here's what the definition of limit says. The punchline is that f of x has to be within epsilon of L. I have to get the distance from f of x to L to be less than epsilon. What does that mean in this case? We know our limit in this case is 5. So this translates into 3x minus 1 minus 5 has to be less than epsilon. What does that mean? That means 3x minus 6 is less than epsilon in absolute value. Well, look, I can factor 3x minus 6. That's 3 times x minus 2 in absolute value. 3 is a positive number, so that can come out of the absolute value sign without any problem. So what I've got is 3 times absolute x minus 2 less than epsilon, or absolute x minus 2, if you divide both sides by 3, less than epsilon over 3. Have you seen this before? The absolute value of x minus 2, also known as the distance from x to 2. The distance from x to 2 is the quantity that we were talking about in the definition of limit over here. The distance from x to a, because a is 2 right now. So now, this is the distance from x to a, and I was looking for delta. My problem is to come up with a delta based on his epsilon, the boss's epsilon. So the boss has picked an epsilon, he hasn't told me what it is, and he wants me to get the distance from 3x minus 1 to 5 to be less than epsilon. I fiddle with that and I come up with, lo and behold, this. So what if I choose delta to be a third of whatever he chose for epsilon? So if he picks epsilon to be 0.01, I divide it by 3 and I say that's how close I need to be. If x is within that much of 2, then just work backwards, and lo and behold, the distance from your function to the limit is less than epsilon. It's a lot of stuff to go through, and probably your head is spinning by now. If you go through this again and again and again, it will eventually make sense. Now, honestly, I've got to tell you, I was a boy math major, and I remember very well struggling with this. And honest to God, I did not understand this stuff until my junior year. But I can also guarantee you that you will not understand it unless you keep hitting it time and time again. And you'll see this again because there are different functions that you have to, different definitions of limit that apply to other kinds of ideas. For example, in Calculus 3, you'll study functions of several variables, and you'll see this definition again where the functions are in a slightly different context, in 2- or 3-dimensional space. But the same idea will happen. You're going to have to take the distance from a function to its limit, its alleged limit, and show that that distance is small. How small? Smaller than the tolerance epsilon, whatever it was, and you have to show that that happens provided that your distance to A is small enough. So the game is, he picks epsilon, we have to make this happen. We get to control the distance from x to A. And the game is, figure out how close to A I have to make x so that the distance from f of x to L becomes less than what he wanted. All right? In the lab, what you will be doing is playing this epsilon-delta game with functions, and you'll have to graph them. And what you'll do is you'll be given particular epsilons, and then your graph will look like something, and you'll take your limit and look at that on the side of your window of the picture. And then imagine going L plus epsilon and L minus epsilon. And a good way to do that is to set the window heights, the vertical limits, to be your L plus epsilon and L minus epsilon. So what you want to do is make sure that the function then does not escape the window. How close do you have to come horizontally? If you keep zooming in, your function will turn not like this where it's escaping, but it will get closer and closer so that it ends up looking more like that. So if the function does not escape the top and bottom, then you found a delta that works. Oh, by the way, when you play this game, some people are tempted to come up with a ridiculous delta, you know. What would happen if you did something like that in the real world? Like, the boss says your parts have to be machined to a certain accuracy. You come up with them machined to this accuracy, even though that's way overkill. You know what'll happen? Well, maybe not. You'll be fired. And you'll be fired because it was a waste of resources to get them machined this accurately if only this accurately would have done. Because it's not for free that you get that kind of accuracy. It costs you something. You had to spend a lot of time and money and machinery and involve a lot of people to get that kind of accuracy. And if only this kind of accuracy was sufficient, then you wasted a lot of resources and they don't need you. Right? So the game is you come up with a delta that works, but just barely. You don't want to waste resources. All right? So that is the idea. I want to do one more argument, give you your money's worth in this lecture. I want to show you how this works in a proof. For example, how do you know that the limit of a sum is the sum of the limits? So if I wanted to prove that the limit as x approaches a of f of x plus g of x is equal to the limit as x approaches a of f of x plus the limit as x approaches a of g of x. How do you know that that's true? Well, here's how we go prove it. We have to start with an epsilon, and we allow the boss to do his worst. And do whatever you want. Choose whatever epsilon you want. So mathematically, we use this very important mathemagical word, let. When we say let epsilon bigger than 0 be given, this is a word of power. This causes a number to exist, epsilon, where it did not exist before. Oh, by the way, notice that epsilon has to be strictly bigger than 0. We do not allow zero tolerance or error of 0. Okay, so epsilon is a positive number, but small. When we say let epsilon be bigger than 0 be given, we are saying let the boss choose whatever he wants for epsilon. Nail it down, write it down. You can cover it up. But once you write it down, I get to come up with the delta based on that epsilon. So let epsilon bigger than 0 be given. I have to show, must show, that the distance from f of x plus g of x to its limit. Well, what is the limit? Well, I never said. I want to assume that these two limits exist. We'll call these L and M. And so the limit that I'm saying is going to work is L plus M, the sum of the two limits. I want to show that that distance is less than epsilon if the distance from x to a is less than delta and bigger than 0. So my job is to come up with this delta based on that epsilon. And I'm assuming that this limit is L and this limit is M. And I've got to show that this limit is L plus M. To do that, I've got to show that the distance from f of x plus g of x to L plus M is less than epsilon. Okay, so what is this distance? Well, let's look at it algebraically. F of x plus g of x minus L plus M. And at this point, we have to do a bunch of algebra, some of which you may not have seen before, but we'll do it. Obviously, this is f of x plus g of x minus L minus m. You have to distribute the minus. Now, if you grew up with Sesame Street like my kids did, then you learn to play the game, what of these two things belongs together? Well, it's obvious that f of x and L belong together because f of x has L as its limit. So I'm going to bring those together. So here's what I'm saying. F of x and L belong together, and I've still got a plus g of x and a minus m. And those things belong together. And it's still true even if I put absolute value signs around this. Okay, now I have to make use of an important property about absolute value that you may or may not have ever seen before. It's a property, a fact, called the triangle inequality. It's difficult to explain why it's called the triangle inequality, but here's the real reason. It's because on a triangle, if you take two sides and add them together, it's always more than the third side. And that fact has lots of different translations, but in this case it's a very simple fact. The triangle inequality says that if you take two numbers like p and q and add them together and take the absolute value, how does that compare to p in absolute value and q in absolute value? Well, if you think about it just a little bit, it should be pretty obvious that it goes this way. If you add p and q together, it's always less than or equal to adding them separately if you took the absolute values. Because after all, if you don't take absolute value, there's going to be some cancellation that might occur here if one of these guys is negative and the other is positive. But if you take the absolute value of each of them and then add, you're going to get the biggest that you possibly can. Of course, if p and q are both positive, there's not going to be any difference. That's fine. I said less than or equal to. And if both of them are negative, then you're going to get the same answer. But if one of them is negative and one of them is positive, this guy is going to be definitely smaller than that. Okay? So I'm going to whip out the triangle inequality on this, where f of x minus L is playing the role of p, and g of x minus m is playing the role of q. So this becomes less than or equal to absolute f of x minus L plus absolute g of x minus m. And I see these a lot. This is the distance from f of x to L. This is the distance from g of x to m. How small are these? Well, the answer is, because the limit is L, I can make these distances as small as I want. What do I need? I want this distance to be smaller than epsilon. So here's my plan. What if I can make this distance smaller than epsilon over 2? And this distance smaller than epsilon over 2. Then when I add them together, I get epsilon over 2 plus epsilon over 2, which would be epsilon, and then I'd be done. The distance that I want here between this guy and that guy would be less than epsilon. Can I make this distance smaller than epsilon over 2? Well, what's epsilon over 2? Well, epsilon is a number that the boss picked. Epsilon over 2, therefore, is half that size. Okay, but it's a number. Can I make the distance from f of x to L less than that number? Sure. If I pick x to be within some number, let's call it delta sub 1. Delta sub 1. Because I'm going to pick another delta here in a minute. But if the distance from x to a is less than delta sub 1, and of course not 0, then I can make the distance from f of x to L smaller than epsilon over 2. So here's how it worked. Because f of x has a limit of L, because it has a limit, that's known, I can make the distance from f of x to L as small as I want. I want to make it smaller than epsilon over 2, so there's got to be a delta that works, a delta that makes that happen. Call that delta 1. If the distance from x to a is smaller than delta 1, or if x is within delta 1 of a, then I can be sure that f of x is within epsilon over 2 of L. But I can do the same thing over here with g. Find a delta 2 so that if x is within delta 2 of a, and of course not 0, not equal to a, then g of x is within epsilon over 2 of m. How do I know that I can do that? Because G has a limit of m. Since G has a limit of m, for every epsilon bigger than 0, I can make the distance from g of x to m smaller than that. I choose this epsilon, epsilon over 2. I'm choosing half of what the boss picked. I can make the distance from g of x to m smaller than that if the distance from x to a is within that much, delta 2. So now I've got these two numbers, delta 1 and delta 2. And what if I make delta, I'm calling a new number, delta, to be the smaller of delta 1 and delta 2? Do you see what's going to happen now? If the distance from x to a is smaller than delta, then automatically the distance from x to a is smaller than delta 1 or equal, and the distance from x to a is smaller than or equal to the delta 2, and that will make both of these true, which makes both of these less than epsilon over 2, which makes the sum less than epsilon, which means that this is less than epsilon, and this is the distance from the sum function to its limit. And I've shown that I can beat the boss's epsilon. I can get the function, the sum function, to be within epsilon of where it's supposed to be, simply by making x this close to a, where this is the smaller of the two deltas that are necessary to make f of x within epsilon over 2 of L and g of x within epsilon over 2 of m. Okay, I told you this wasn't going to be easy. The good news is you are not going to have to be able to do this kind of stuff now. Some of you, in a few years, yes, you would have to do this, but right now, your job is to simply try to understand it. Try to understand it, okay? Don't just space it off. You can go through this. The problems for Monday will be much more specific. They're going to be more like this kind of thing. Given the epsilon that I said, epsilon being, well, in this case, actually it's not even that one, this one, where I gave you the epsilon as 1/2. In that case, what do you have to come up with to make it work? So most of the problems that you have to play with are graphical. You're looking at it, this is your epsilon, how close do you have to get this way? So you get used to doing that. Then some of them are analytical, algebraic. You have to come up with some equations and solve and figure out which one it is that's the smaller of the two, and that's the delta. Kind of like what I did a minute ago, only much more abstractly and much more generally. Okay, so don't panic, but please do look at this again sometime, and I think it will stretch your mind and you'll be able to think a little bit differently. I think on Thursday of next week in the lab, things will start settling down a little bit more if we can struggle through playing the epsilon-delta game. Okay, have a good weekend.